Good morning, everyone. My name is Dongjun Kim. I am a PhD student of Korea University. Today, I'll talk about characterization of elastic-plastic reactive stress field under load and displacement control. In this presentation, I checked the existing estimation on reactive stress field, and I proposed new equation. The procedure of presentation is as follows. And as you know, for the plant structure under a high temperature operating conditions, it is important to consider creep behavior. And existing nuclear plant operates under high temperature and high pressure. This condition causes to state-state creep. But generation 4 nuclear plant, for example SFR, is operate under high temperature and low pressure. This condition causes transient creep during operation. Then is increasing the importance of research on material behavior on the transient creep for the structure assessment of the nuclear plant. So I start study on transient creep behavior. I will introduce briefly reactive stress field estimation. In linear elastic fracture mechanics, Kn using the stress intensity factor K and T stress is proposed. And in elastic plastic fracture mechanics, HR field and Q stress is proposed to estimation on reactive stress field. And in time-dependent fracture mechanics, RR field is defined C star from C star, and Q stress is proposed. But this equation is applied under steady-state creep. Then, to estimate reactive stress field in transient creep, CT integral is used, and this equation is RR field is defined as CT integral. But this equation cannot consider the constant effect. Then, using the reference stress and theta Q term is proposed to estimate reactive stress field with considering constant effect. And this equation is this method equation. But this has to consider the effect of plastic exponent, and it is need to calculate CT integral for estimating the reactive stress field. Now, firstly, I checked the existing estimation equation from comparing with FE analysis. And from comparing results, I analyzed the applicable and improbable point of estimation equation. And I consider SEB specimen in this FE analysis. As material property, elastic plastic is applied, and for plastic behavior, Lemberg-Oskar equation is used, and for creep behavior, Haro is applied. And this table shows the detailed information. I will talk about FE modeling and analysis. Elastic plastic FE analysis is performed using abacus. And as loading condition, load control or displacement control are each applied. And this figure shows the used FE model and boundary condition. And edge meshing was used to describe the corrective. And for validation of FE mesh to calculate the CT integral, elastic FE analysis is performed. At short time, value of a CT integral should satisfy this relationship. And from the definition of CT integral, the value of CT were extracted from the second control. And this figure shows the FE mesh used in the present work can provide accurate CT integral values. This slide shows the result of the existing estimation on corrective stress field. Upper part shows at the stress field at initial time. In other words, is elastic state. And bottom part shows the corrective stress field under elastic creep with bottom part shows the corrective stress field under elastic creep. The symbol, each symbol is reference field and line is FE result. And except this figure, other figure shows a good agreement to estimate corrective stress field. This figure shows the existing stress estimation equation is cannot consider the effect of plasticity. This case is plasticity exponent rather than creep exponent. This is there we can see the mismatch between the reference field and FE result. And we use this equation. For using this equation, we calculate CT from the FE analysis. But for more simple method, we check the CT estimation equation is checked. For validity of CT estimation, we compared the FE result and with existing CT estimation. Upper part is for loading control cases, and bottom part is for displacement control case. This figure shows existing CT estimation has limitation when m unequal n case. Objective. Existing equation for estimating corrective stress field has some limitation. So in this paper, to improve the limitation, I propose we use equations to characterize the corrective stress field on the transient creep using a modification of the existing equations. Using equation is HRF field, RF field, and estimation equation for CT integral. To verify the proposed equation, I compared with the results of FE analysis. This slide and next slide shows the process of derivation of the proposed equation under load control case. Proposed equation is derived from the modification of the existing formula for correct stress field. This content is modification. And process derivation is as follows. And in processing of derivation, I assume that the equation equals HR field when it is initial time. And finally, I propose this equation. This equation has a limitation for m equal 10 and n equal 5 and larger loading amplitude. This condition we propose with fitting equation using FI analysis. This slide shows the proposed equation for correct stress field under displacement control. The process of derivation under displacement control is similar to process under load control condition. And final proposed equation is this. Is this also modification of existing city estimation? Before comparison of proposed equation with FE analysis, I estimate Z factor. Z factor is elastic follow factor, and this factor is needed to characterize second stress loading condition. And in this paper, I define Z factor to comparing FE results with the existing equation of a CT integral under secondary loading condition. And this figure and this table is shown the determine Z factor. And this slide is start to show the comparison result, the proposed equation and FE result. Upper part is load control case, and bottom part is for displacement control case. This slide is both M and N equal 5 case. This case shows line is proposed equation and symbol is FE result with loading amplitude. And this figure shows the proposed equation is good agreement with FE result. And this slide shows when M equal N equal 10 case. This case also good agreement result. This slide shows in M unequal N case, and this case is M equal 5 and N equal 10 case. This case also good agreement result, comparison result. And in this case, M equal 10 and N equal 5 case. This case, in displacement control case, is good agreement result. And this case is, before I set the limitation, small loading condition. In small loading condition is good agreement proposed equation, and this large loading condition we proposed fitting equation from this FE analysis. Conclusion: I checked the existing equation of one corrective stress field, and I propose the equation to characterize corrective stress field under elastic conditions using a modification of the existing equations. For verifying the proposed equation, I performed 2D FE analysis for SEB specimen, and we checked that the using proposed equation can characterize the corrective stress field. And ongoing works, we will various models can be considering because consider the various constraint effects. And for studying about we will have more study about cross effects on transient quick behavior. And another research is mismatch effect on corrective stress field will be studied. Thank you.